Hi everyone, and super glad to be speaking in front of all of you. I am Aurimas, Chief Product Officer at Neptune.AI, and today I want to talk about a few things around observability in LLMOps pipeline. I want to focus specifically on the infrastructure-related problems in the actual observability stack throughout the pipeline. The goal of this talk is to kind of help you enhance your mental model when you think around the systems that you will need to build around observability in your LLM applications, LLM-based applications, and what impact it might have on, for example, your spend. Because I will be basing the talk around an assumption that you're building for production. So for production, you definitely need to have observability and monitoring. So just to quickly rehash the LLMOps pipeline, we have pre-training, so training of foundation models, then some reinforcement learning with human feedback, fine-tuning, which together we are used to calling post-training, some prompt engineering work, some maybe simple RAG-based applications, then some agents going forward, and eventually, not there yet, but maybe we'll be seeing some of the agentic network applications as well, where multi-agent systems communicate with each other to produce some result. So the goal of this presentation is to go through this curve to kind of construct your own internal mental model, because you might be building in part of this pipeline. It is useful to split it into, maybe I'll go back, split it into a few parts. So you're either building the foundation model itself, or you're usually building a application which is built on top of already existing LLM. So today we are somewhere here. We are talking a lot about agents. We are implementing agents in some specific applications like customer support and similar. But I think that the full potential of agents might be implemented by the end of the year, this year, but also a question mark. And the agentic networks is a prediction. It would be nice to have it by the end of 2025, but I think that we will be focusing quite a lot on building stronger agents rather than having multiple agents actually communicating with each other. But it's a very nice thing to think about, and hopefully we'll move into that space as well. So two pieces, either you are actually training your own foundation model or you are building on top of the foundation model. And I'll be splitting this presentation in these two pieces as well. So we as a company at Neptune, we are really focusing on the pre-training piece. So we have two initial boxes. So let's start with the pre-training of large language models and what kind of observability challenges we face here. So we kind of started thinking, so we are an experiment tracker as a company, but we kind of started thinking of experiment tracker in large language model training more of a experiment monitoring or experiment observability platform, because the needs are now different. And they are driven by multiple scale influencers that we are observing. So the size of GPU clusters that are being used, the model sizes that are being trained, and the amount of time, training time that it takes to actually train the model. So the few main problems is that we only can train a large language model, the base model, once. So we cannot really fail because we cannot restart a model training which is taking, let's say, 2 months to complete. We are running on huge clusters. So we are talking here about nowadays thousands to tens of thousands GPU clusters that cost throughout the training time tens to hundreds of millions of dollars. And as we move through time, these GPUs or clusters of GPUs start failing. And even with the best architecture, we currently kind of know that for a new cluster which is of huge size, let's say 100,000 GPUs, we can expect really often failures, like a purely new cluster can fail every 20 or 30 minutes, at least one GPU would. And it's driven by multiple factors, networking and the GPU itself. But naturally, some of the companies, the biggest companies, are trying to fight back, and they are implementing advanced algorithms to restart the training runs and move the weights between GPUs and do checkpointing without necessarily stopping the training run. But still, there are costs. So if a GPU fails, you need to restart your training run from a few steps in the past, and that usually can cost you, if it's a few hours, maybe $1 million, right? And then once you move forward, you are accumulating this cost. So there's quite a lot of healthy paranoia when it comes to how you are observing these kinds of systems. So if you would look into how many parameters we are seeing companies track over time, parameters meaning metrics accumulated through your training run, they are naturally correlating with the size of the model itself. So the bigger the model, the more you want to track. Usually you want to do that in different hidden layers. Usually, because the restarts cost so much, you also want to track exploding amount of unique metrics per hidden layer. So since it's correlating, you can kind of draw this line, and it is similar to the amount of, to the size of the model, so the amount of parameters the model has. But in extreme use cases, companies also want to track metrics per GPU. So imagine if you're training on 10,000 GPU cluster, you are tracking 10,000 times more unique metrics per step. So that explodes in amount. So basically, what the experiment trackers of today actually are, these are really big data analytics systems, and you need to be able to ingest data at scale and visualize data at scale as you ingest it. So how you construct these systems is different, and how much you pay for these systems is different as well. So if you're planning to go into LLM training from scratch, make sure that you take this into account. So moving on to reinforcement learning with human feedback, it's a little bit simpler. You do some supervised fine-tuning on the base model, and then you create your reward model and use it to optimize your large language models policy. Now, usually in these types of processes, the cost is 10x less. So you're probably training on not 10,000 GPU clusters of 10,000, but rather 1,000. And you're not training for a month. You're usually training for days or weeks. The bigger part of the cost that you will incur here is not necessarily the observability infrastructure itself, but rather human cost of how much it will cost to label the data and actually prepare the data sets to train your own models, reward models, and then apply the policy optimization. I will not focus a lot on fine-tuning. It is a big topic. So right here, I'm pointing to initial fine-tuning. So how you create your first application. Usually it's just some very easy experiment tracking. You don't necessarily have your own evaluator models prepared, but that also is not something that I would suggest. Like proper fine-tuning involves having your own reward model prepared for evaluation. Moving to very simple agentic systems. So we already have a large language model ready, and then you want to build your Gen AI-based systems on top of already pre-trained and fine-tuned large language model. So very simple, very naive RAG application. You have a controller facing your chat interface. Usually that controller runs a framework like Llama Index or LangChain, and then it controls all of the flow, right? So you have your retrieval, you have your generation, and 1 year ago, an observability in these kinds of systems would probably be just looking into the inputs and outputs of it and running some evals against that, trying to score for, let's say, toxicity or other qualities in your outputs. Today, in the past year, we evolved into thinking about tracing and instrumenting your application. So that's what we do in modern Gen AI system observability. So we collect spans of your application. So in this very simple case, you would have just construction of query, embedding your query into a vector, querying a database, constructing a final prompt that is fed to your LLM for generation use cases, and then getting the answer. So the problem is that it looks very simple, but the data amount that you actually produce in these kinds of application is not that trivial. So one is that you need to have all of the spans inside of your trace, but you also then need to perform some evaluation on a span level. And it's no longer just evaluating the inputs and outputs of the entire trace, right? So you might be running some different types of evaluations or just monitoring on your system. Sometimes you just want to see if the vectors returned by your search are relevant for your query, or you want to evaluate the final answer that is returned to your application. And even more, currently the most popular way of doing it is probably using another large language model to kind of act as a judge for your outputs or evaluate different qualities of the output that are produced by your system. Now, this also might look simple, but there are a few moving pieces that need to be taken care of. You will need to, apart from tracing all of these spans, you will also need to efficiently and reliably run the evaluations, right? So they are currently mostly being done inside of platforms that collect these traces. So it is a lot easier because you can restart your evaluation runs if they break, but you can actually build reliable systems. So that's not a big problem. But if you would move evaluations closer to your application, it can impact the application performance. You can start breaking your application, and similar problems can occur. So it's not really as simple as it looks. Now, moving to agents, there are multiple definitions of agents, but the kind of high-level mind model that you can use is that you're just taking the retrieval piece, you are kind of calling it knowledge, you're moving the LLM as a core of your application, so it basically becomes the controller, and then you give it power to decide on how your application has to behave. It can be very simple things like branching strategies or actually running a loop inside the controller so that it makes sure that your desired result, the intent that is provided by a user, is completed. It might run out of track, so usually we are currently just kind of focusing on these guardrailed use cases where we are controlling how the agent behaves instead of letting it loose completely and then basically making it unreliable. So on top of it, oh sorry, wrong button. On top of it, we add long memory, so something very similar to actual knowledge, but instead of having external knowledge about some context, you simply feed your historical interactions in a similar way to some storage. It can be vector storage, it can be graph storage, or a mix. Usually you have some more complicated, more complex construction of how you extract the data from the memory so that it fits your queries, but it's very similar to knowledge. Then you have tools, and you have instruction sets on how the agent should behave in certain cases. And you add an interface so that you can actually communicate with it. So the problem with that is, with this architecture, is that first, the actual chain is non-deterministic anymore. In very simple And very simple agents, it is still deterministic when we are actually guardrailing it properly. But if we are doing any loops inside the controller, it is becoming a problem because the actual chain is non-deterministic, and we need to then trace each of these elements into a single, trace each of these elements and connect their spans into a single chain. Now, as mentioned, the problems are that the time it takes to complete is non-deterministic, the amount of spans it produces is non-deterministic, the length of a trace it produces is non-deterministic. So it explodes the amount of data that is being stored even further, and you need to run non-deterministic amounts of evaluations to make sure that your agent is behaving as you expect. And then moving forward to the agentic networks, so distributed agent applications where a central agent or a graph of agents are communicating between each other to produce the final result. So we take the agent, previously defined one, and we multiply it a few times, and we allow these agents to communicate with each other. And we provide some user interface that can trigger some actions to it. So there are a few. So this is not yet, I would say, I believe that it's not yet done in practice properly. And to be honest, it might not be done in practice unless we actually run into some issues of creating really powerful base agents and really need to create one stronger agent that can kind of give commands to weaker agents. So use cases would be a CEO agent commanding marketing agents and sales agents to run a organization. But it is a little bit fiction today, but hopefully in a year or two we might find a use case for it. I think currently we are good enough with just strong core agents that can perform all of it in a single application. Why? Because, well, there are difficulties on how you actually would treat such an agentic system and more specifically observe it. I do believe that eventually we'll find and move software engineering patterns to these kinds of applications because agents are generally just microservices, right? Because we are powered by some core LLM, but eventually we are just applications that take in some input and provide some output or do some action. So again, in order to properly observe and instrument such a system, we kind of need to not only connect all of the spans inside of a single application, but we need to somehow connect in time all of the communications that are happening through the agents and connect them into a single trace in the end. So a very simplest way of doing it might seem just sending a unique identifier as you send an intent to the first proxy to the system, and then just send that ID around. But it's not as easy as it sounds because applications do break, and usually in these kinds of systems, you wouldn't have just a single agent sitting there and doing work, so you would have copies of agents so that you can load balance between agents, and you always have some availability when you're actually hitting one of the interfaces of an agent, so that you don't slow the entire or just stop the entire system altogether from acting. So I think that we'll start seeing distributed microservice type of patterns coming up in these kinds of systems. So we'll probably see something similar like service mesh. Maybe it will be coined agent mesh eventually. So we would be facing each of agent with some proxy gateway that would manage the traffic, would manage proper restarts, making sure that trace IDs are properly sent throughout the applications and then properly tracked in our observability systems. Or we'll see something more similar to event-based architectures where the actions and requests between agents would be routed through queues, distributed queues, and restarted as needed. So agents would become actual consumers of these queues instead of exposing their endpoints for synchronous communication. So getting back to the complexities of these kinds of systems, so now you have not only one non-deterministic application that constructs a trace of a non-deterministic size. You actually have 3 in this case, but it could be a lot more, and then each of them are unbound in length, unbound in the amount of spans comprising them, and again, you need to run evaluations and monitoring on each of a span. So these kind of systems really are becoming, again, big data analytics systems, because you might think that it's enough to just have the data in the system, but actually what you really want to also do is to attach some advanced metadata to the spans so that you can then group your data and visualize the behavior through time and properly observe your applications, because observability is not just about having the data in the system, it's also being able to run some analytics on top of it once you have it. So that's the main gist of what I wanted to talk about. Just to remind everyone, this is the curve that I was talking about. And we, as a company, Neptune, are focusing on the first 3 boxes of this diagram, and in the recent years we actually rebuilt our system quite a lot, because we understood the need of the companies that are actually training their own foundation models, and the need is really about the scale. The scale is multidimensional, so you need to ingest a lot of data, you need to visualize a lot of data in a very fast way, and you also need to make the data findable, and you need to allow the user to create visualizations on top of that data. Because for the companies that train their own foundation models, the main resource is the researcher who's doing the research, and they are really spending a lot of time just watching how the experiments are behaving and coming up with new ideas. And you need to give them something that is fast and able to handle all of the data. So if you want to catch up with us, we are at the booth 238. We have some coconuts, so if you are thirsty and want something cold to drink, be sure to drop by. If you want to discuss some things that we just saw in the presentation, also feel free to drop by and let's have a discussion. Yep.
Thank you, Aurimas. If you have a question, Samara on stage left has a microphone. Make eye contact with her and get your question asked. So she's the one that you want to make eye contact with. There's a couple of questions I see by stage.
Hello.
Yes.
Yeah. Aurimas, thanks for the presentation. Over here.
It's very light. It's very light.
Over here, to your left.
To my left. Oh, hi. Yeah.
Yeah. So observability is one thing, right? So obviously you need a lot of infrastructure to collect all this data. As you said, it's like a big data kind of problem. But what about, I mean, you do that to basically make inferences. So how do you know if your model has gotten better or not? Because at its heart, each of them is probabilistic. Right. So do you guys do anything to help me understand if whatever new model, let's say we upgraded to Llama 3.1. So now is it better or worse? Like, what are some of the metrics we use?
So what you're probably referring to is when you're building a system, you built it out already, and then you swap a model underneath it.
So going back to a software engineer's discipline of doing like regression testing,
Yeah.
Now, is this model better or not? But we can't use those techniques because the system is inherently probabilistic.
So for the initial evaluation phase, it is pretty easy. It's not complicated. You have your evaluations ready. Usually it's some internal evaluations, so not something publicly available. But that's not how you do production evaluation. Usually how you do it is just you deploy two systems next to each other. And that's also where it is very important that you properly attach the metadata to the traces that you produce so that you can then through time draw the curves of how these models behave. But you don't want to stop the previous model usually. You want to run them both for some time to see how your evaluation metrics behave in time. And that's how you usually do it, not complicated. And evaluations, topic of evaluations themselves, like it's a hot topic. So either you create your internal ones or just use some of the shelf.
One more question.
I have like two small questions within it was like the first one is for the rack. When during the span of the evaluate step, like do we need to have it synchronously, like or it can be like asynchronously that together with other span? So that's number one questions. Number two question is that you touched briefly about that for the agent network. The future is to have the agent communicate via message queue. Actually, we also strongly believe in it, but I'm just not sure is there any company successfully deploy the message queue based communication between different agents, and during that implementation, what you see be the challenges that those companies face?
The first one was about spans and evaluations.
The span for the evaluation for the rack.
Usually the evaluation itself is not a span, right? You have your spans stored asynchronously. That's today's world, right? You store your spans asynchronously and usually you run evaluations in the platform itself. There are some libraries that provide you real-time evaluations, so you would run them as your application runs as well, but it's pretty destructive if something goes wrong, right? So usually it's best to do it asynchronously and then just run it offline.
Yeah, the second question is about the agent network communication using message queue.
And is it like the first question is clear? Or?
Oh yeah, it's clear. It's just the chart that you draw is like, it looked to me that synchronously, but yeah, I remember it can be done asynchronously. Yeah.
Yeah. So for agentic networks. And when it comes to managing them through queues, right? That was the main problem. So it's actually very similar to what you would do with just sending the ID around, right? You can just send a request and then attach the ID to it. So I think that the main issue is really the apps misbehaving and going down. So if you're implementing, let's say, real-time instrumentation or tracing, you can have a agent pick up the message from the queue. It has its own, it has the correct ID, so you can kind of connect the spans from different agents into one trace using that ID. But what happens if that agent goes down and restarts, right? You probably already have the traces and spans in the system, and then you're restarting the job, and then you're kind of duplicating the data.
Oh, okay, got it.
So it's not solved yet. I think it's maybe the future, but it's not yet there. So people are just experimenting with it. And when it comes to tracing of these kinds of systems, there are still many distributed system challenges to solve, I think. So I think that these patterns will be what will be implemented, but I don't believe anyone has successfully, properly productionized it yet.
Okay, thank you.
I just want